Today we're going to look at some arithmetic that we can do with radicals. So we looked a little bit last lecture at how we could think of radicals as exponents, and since we can think of radicals as exponents, as rational exponents, it turns out we have some rules that we can use with them that typically apply to exponents. And one of those in particular is the fact that if you have an exponent that is raised to some product of something, so for example, if you have a product like this and it's raised to some exponent power, well, as long as these are separated by multiplication or division, we can distribute that exponent, and this will become p to the n, p to the q to the n in this particular case. So p times q to the n is equal to p to the n times q to the n. So since something like this, the square root of 4xy, we could really just think of this as 4xy to the 1/2 power. Again, I can think of distributing this 1/2 like so. Since they're all separated by multiplication, I can get 4 to the 1/2 times x to the 1/2 times y to the 1/2. Or I could have just thought of this as the square root of 4 times the square root of x times the square root of y. So since the radical sign, square root in this case, could be thought of as an exponent, we can in fact break it up like this when it's over something that's being multiplied or something that is being divided. So the case when this comes in handy is if we want to take a radical expression and simplify it a little bit. So we'll start with a really basic example. We'll start with something like this, the square root of 8. I'm actually going to rewrite this so that's not square root of 8, but I'm going to simplify this as much as possible. Because I know within here I might be able to get some factors out, or get some parts of this out to the front of the radical side. So here's what I'm going to do. I'm actually going to think of this as, instead of 8, I'm thinking of this as 2 times 2 times 2. And in fact, since this is a square root, I know that the square root of 4 is just 2. So I can actually think of splitting this up into the square root of 2 times 2 times the square root of 2. So I'm actually splitting up my multiplication under the radical sign. So I end up getting the square root of 4 times the square root of 2. But the square root of 4 I know is just 2. So it turns out that the square root of 8 could be simplified to 2 times the square root of 2. This is the kind of thing we talk about that we mean when we talk about simplifying radical expressions. Getting everything that we can, all the integers, out of the radical expression. Now this also applies to expressions that aren't just integers. So for example, something like this, the square root of 32 times x to the 3rd power times y to the 4th power. Well, I know here that 32 is really 16 times 2. I know I can split that up and maybe take the square root of 16 because that's 4, I know that. Also, if I'm taking the square root of x to the 3rd, that means there's an x squared in there that I can maybe pull out and take the square root of the x squared. And then if the square root of y to the 4th, that'll actually just be y squared. So I'm just going to go ahead and break this up into 3 parts. This will be the square root of 32 times the square root of x cubed times the square root of y to the 4th. Alright, so now within the 32, I know I could split this up into the square root of 16 times 2. In the square root of x cubed, I could split this up into the square root of x cubed times x. And then here, I could actually split this up into the square root. Well, you know what? I don't even need to do this one because I know the square root of y to the 4th is just going to be y squared. So I can go ahead and take that, since y squared times y squared should give me y to the 4th. But here, again, I can split the radical. This would really just be the square root of 16 times the square root of 2. So the square root of 16 is 4. And then I have the square root of 2 left over. The square root of x squared, now be careful here, we actually write this as the absolute value of x. And the reason we do this is because we know it has to be a positive value because we're squaring the x first. And when we take the square root, we tend to take the positive values. Also, this comes in handy when we're solving equations. This allows us to take the positive and the negative version of the answer. For example, in something like this, if I have an equation where this x squared is equal to 4, and then I take the square root of both sides, well, in order to get the positive and negative version of the answer, right, because I can square positive 2 or negative 2 and get 4, well, I interpret this square root of x squared as the absolute value of x, and then the square root of 4 is 2, and then I'll get x is equal to 2 or negative 2 when I split up my absolute value. So that's the reason we do that here. So just be careful. Anytime you have a square root of something to the second power, it always becomes the absolute value of that power. The same thing for the fourth root of something to the fourth power. It would be the absolute value. We don't worry about with odd powers because odd powers can be positive and negative. So that one doesn't matter so much. With the even powers, it definitely does matter. Let's look at another quick example. So how about the cubed root of 81 over x to the fourth y squared? Now again, this is separated by division, so I can actually think of just taking this, the cubed root of 81 over cubed root of x to the fourth, and then the cubed root of y squared, each of these individually. Well, what is 81? 81 is 3 to the fourth power. So really I can think of it as 3 cubed times 3, which would be 27 times 3. So this is really the cubed root of 27 times 3. The cubed root of x to the fourth is really just x cubed times x. And then cubed root of y to the second power, there's not enough y's here for us to take the cubed root of anything, so we're just going to leave him kind of as is. We're not going to simplify him. Okay, so now what can I do? Well, I can say this cubed root will also distribute over 27 and 3, so the cubed root of 27 is just 3, and then I'm left with the cubed root of 3, which can't be simplified, or it's we don't know exactly what it is, so we're just going to leave it in this form, which is a very exact way of writing it. We're not going to estimate it with a calculator or anything like that. And then here I can distribute this cubed root of x cubed, so that will become x, and then I have the cubed root of x left over, and then I'll just have the cubed root of y squared like this. If I wanted to, I could even make this maybe a little nicer. I could pull the 3 over x out to the front, and then undistribute the cubed root of 3, and this will just be the cubed root of 3 over x times y squared. So maybe that's a little neater looking version of this. Again, I didn't have to do the absolute value here when I took the cubed root of x cubed, because you can cube something and get a negative or a positive, so we're not too concerned about that, only with the even powers. So when we're dealing with radicals, they'll add and subtract the same way you might add and subtract common terms. So if I have something like this, 2 times the square root of 5 minus 7 times the square root of 5, you can kind of think of this as the same ways as 2 times x minus 7 times x. Because really, what are you doing? 2 times square root of 5 means you have 2 square roots of 5, and then 7 times square root of 5 means that you have 7 square roots of 5. When you subtract them, you'll have negative 5 square roots of 5, or negative 5 times the square root of 5. So we can do addition and subtraction with these radicals relatively easy. Now, of course, if you have something like this, 2 times the square root of 3 plus 4 times the fourth root of 3 minus 4 times the square root of 3. The only two that will combine in this case are the square roots of 3. The fourth root of 3 is not the same thing, it's a different number. So in this case I can combine the 2 root 3 minus 4 root 3, and I'll get minus 2 root 3, and then plus 4, the fourth root of 3, that has to stay like it was. So we can't combine these two together. This is as simplified as we can get with this particular expression. So that's how addition and subtraction will work with these. With multiplication, it's a little different. For example, if I have the square root of 3 times the square root of 5, well, I already said that you could think about distributing a square root over multiplication. Well, you can do the opposite way as well, right? If this is the square root of 3 times the square root of 5, I could really just think of this as the square root of 3 times 5, because I could go back and distribute this square root and get back to this particular point. So this is totally fine. There's no problem with this. So really I can think of this as the square root of 15. Same thing with division. So if I'm taking the square roots of 3 divided by the square root of 2, for example, I can really just rewrite this as the square root of 3 divided by 2, so the square root of 1 1/2. Now, the nice thing here is that even if these aren't the same radical types, I can still possibly do some combinations. It depends on what the base is. So if I could take something like this, the square root of x times the fourth root of x, and I can actually combine these, because if I rewrite these in terms of an exponent, this will be x to the 1/2 power, this will be x to the 1/4 power. I end up multiplying two terms that are exactly the same base, so I can end up just adding the exponents here. So this will really be 1/2 plus 1/4, so 1/2 is really 2/4, so this will really be x to the 3/4 power. And then if I want to rewrite this into an exponent, if I want to rewrite this into a radical, I can just think of this as x cubed to the 1/4 power, and then I'll get x cubed and then the fourth root of all of that, since all of that to the 1/4 power is the same thing as saying the fourth root of x cubed. Now be careful, the only way this actually works is when both of these bases are exactly the same. If these had been different bases, an x and a y, for example, I would have been stuck. I wouldn't have been able to combine at this point, because when I turned them into exponents, I wouldn't have had similar bases. I wouldn't have been able to add the exponents together for this. So we can also do some foiling with these terms. For example, if I have something like 4 plus the square root of 5 times 3 minus the square root of 2, if I take an expression like this, 4 plus the square root of 5 won't combine, so this is as simple as I can get this particular expression. Well, I can still foil this. I can still take the first times the first, then I can take the outer two times each other, the inner two times each other, and then the last two times each other. So 4 times 3 will be 12. 4 times negative square root of 2 will be minus 4 times the square root of 2. Square root of 5 times 3, this will be plus 3 times the square root of 5. And then square root of 5 times negative square root of 2, this will be a negative square root of 10. Because remember, when you're multiplying two radicals and they're exactly the same radicals, in this case square root, you can add you can multiply the parts that are underneath the radical. In this case, I can multiply the 5 times the 2. And then the last thing I want to do is look up here and see does anything simplify. In this case, I can only add and subtract radicals when they're exactly the same. So square root of 2 is not the same as the square root of 5, which is not the same as the square root of 10, so I can't actually put any of these together in this particular case. But let's see a different one. How about something like this? 2 plus the square root of 3 times 2 minus the square root of 3. These two expressions have a special characteristic, and I'll talk about what these are in a second. But first, let's see what happens when we multiply these. Well, again, I'll just do FOIL. So 2 times 2 is 4. 2 times the negative square root of 3 is negative 2 times the square root of 3. 2 times the positive square root of 3 is 2 times positive square root of 3. And then square root of 3 times square root of 3, that will be square root of 3 squared, which will just be square root of 9, which will just be 3. So in this case, you'll see that if you multiply the two radicals if you multiply two square roots, and they have the exact same number underneath, they'll actually end up canceling each other out. So this will actually just turn into minus 3, or minus the square root of 3 squared. And then the last thing you'll see here is that this will actually cancel out, right? Negative 2 root 3 plus 2 root 3. And then I'm just left with 4 minus 3, so I'm left with 1. Now, if you ever set one up like this, where you have the exact same two terms in the expression, and the only thing that's different is there's a plus here and a minus here, so a plus here and a minus here in this particular case, then what will happen is the radical parts will always go away, because the 2 in the middle will cancel out like this, and then the one that you get from the end, by multiplying these two together, the square root will end up going away because you're multiplying the same two square roots together. So we have a term for this. Anytime that you take two expressions like this, and the only thing that's different in these binomial, in these expressions with two terms, the only thing that's different is the addition and the subtraction. We call these conjugates. So for example, if I gave you something like this, 4 minus the square root of 3, and I said, what is the conjugate of 4 minus the square root of 3? Then the only thing you have to do is say, oh, 4 plus the square root of 3. That would be the conjugate of this particular term, or this particular expression. And you'll see that the same thing will happen here if I multiply these two terms together, these two expressions together. I'll take 4 times 4, which is 16. 4 times square root of 3 is 4 times the square root of 3. And then negative square root of 3 times 4 is minus 4 times the square root of 3. And then square root of 3 times square root of 3, that will be the square root of 3 squared, which will just be 3. So I'm getting minus 3 here. Again, this will cancel out and this will cancel out, and I'm just left with 16 minus 3, which is equal to 13. Now, the reason that conjugates are important for us is because they're a tool that allow us to remove some radicals out of certain parts where we don't necessarily want them in an expression. One of these places that we typically don't want to put radicals is in the denominator of a fraction. The way we just tend not to write them there. So typically if we have, for example, something like this, an expression where we have a radical in the denominator of that fraction, we want to remove this. This is called rationalizing the denominator. So we're going to rationalize this denominator. In other words, we're going to remove all of the radicals from the denominator. Now, the easiest way to do this would just be to multiply the square root of 3 times the square root of 3, right? Because that will just become 3, which is perfectly fine to have in our denominator. Now, of course, this is a fraction, so if I do that to the bottom, I have to always do this to the top as well. So this will just become 5 times the square root of 3 over 3. And typically we're fine with having a radical in the numerator of the fraction, just not in the denominator. So whenever we have an expression like that that only has one radical down there, a single term expression, something like 7 over the square root of x, well, we can just go by and multiply by whatever that denominator actually is. So just multiply square root of x times the square root of x, do it to the top as well. I end up with 7 square root of x all over just x. And that's how we would rationalize an expression like this. Now, the reason that conjugates come into play in rationalizing a denominator is if we have something like this. What if I had this expression? So 3 over the square root of 5 plus 3, all in the denominator. Well, if I just went through and multiplied this by the square root of 5, like I did before to try to just get rid of those radicals by just multiplying by whatever the radical was, well, I'd end up with 3 root 5 in the numerator, and in the denominator I would have to distribute this square root of 5, so square root of 5 times square root of 5 would be 5, but then square root of 5 times 3 would just be 3 times square root of 5, and I didn't solve any problems. I'm still left with a radical expression in the denominator of my fraction. So what I'm going to do instead is I know that if I multiply this by its conjugate, it will, all the radical parts of the expression should go away, and I should end up with just a constant in the bottom, or I should say a non-radical constant in the denominator of my fraction. So that's what I'm going to do. I'm going to multiply this by its conjugate, which will be square root of 5 minus 3. And of course you have to do that to the top as well. Now when I multiply this together, I'll FOIL this. Square root of 5 times square root of 5 is 5. Square root of 5 times 3 will be 3 times the square root of 5. Square root of 5 times negative 3 will be minus 3 times the square root of 5. And then 3 times negative 3 will just be negative 9. And then up here in the top, I have to distribute this to both parts of the expression, so be careful that you distribute out. And I'll end up getting 3 times the square root of 5 minus 9. And then here in the bottom, this plus 3 square root of 5 and the minus 3 square root of 5 will go away. And I'll end up getting 3 square root of 5 minus 9 over 5 minus 9, which is negative 4. And this would be a example of a rationalized denominator because it does not have any radicals in the denominator. We'll try one more. Something like this, 2 plus the square root of 7 over 5 minus the square root of 2. Again, I don't care necessarily about getting rid of the radicals in the numerator. I definitely want to get rid of radicals in the denominator. So I'll multiply this by its conjugate, which would be 5 plus the square root of 2. Again, all you have to change is the sign in the middle. And then I have to also multiply by 5 plus the square root of 2 in the numerator. So in the bottom, hopefully you're picking up now that all I really have to multiply is the first term times the first term and the last term times the last term, because the middle two are going to go away, the outer and the inner term. So this will be 5 times 5, which is 25. And then the square root of 2 times square root of 2 is just 2, and it will be negative, since this is negative times a positive. So minus 2. In the top, these are not conjugates, so I do have to FOIL this completely out. 2 times 5 is 10. 2 times square root of 2 is 2 root 2. 5 times the square root of 7 is 5 square root of 7. And then square root of 7 times square root of 2 will be square root of 14. And then I would just keep simplifying this. In the top, nothing will combine because they're all different square roots. So I'll just leave this as 10 plus 2 root 2 plus 5 times the square root of 7 plus the square root of 14, and then all of that over 23. And it looks like a more complicated expression. It kind of is, but the idea was that we got all of the radicals out of the denominator. We rationalized the denominator.